Yeah, thank you. It's been a really great conference, and I felt truly sort of honored to have been invited. So thank you very much. So yeah, I want to talk. I feel like I have a lot to live up to because I've had multiple people reference and like allude to my talk. So hopefully that you all find my talk interesting and you learn something from it. By the way, it's more of a survey talk. So if you find something I'm saying not interesting or anything like this, you can tune me off like 5 to 8 minutes, and then I'll be talking about something else. So yeah, that should work fine. So yeah, I want to talk about just a perspective, because perspectives on moments of L functions. I want to talk about my perspective, a rather small and limited one, on large sieves, and in particular on this thing that Jesse and Alex have alluded to about sort of quasi-orthogonality in large sieves. So I figured a good place to start would just be about large sieves in general. So I was encouraged to give a gentle introduction. So I want to talk about yeah, just what is a large sieve in general, and kind of how do we think about this. So in general, let's say I have some finite set of, let's say F harmonics. Let's say it's a discrete set. You can consider continuous families of harmonics, but we'll just consider discrete sets. And a general large sieve inequality is just an inequality like this. Really, it's a bound on like the square of the operator norm of this particular linear operator. Okay, nothing particularly new to a lot of you in the audience. I'll just make some initial observations about yeah, this sort of orthogonality or quasi-orthogonality condition and kind of where it comes from. So first of all, if I just take my sum and I open up the square and I interchange the order of summation, because man, we love to do that as analytic number theorists, we just can't get enough of it. And I look at just the diagonal contributions when n1 and n2 are the same. I'm just going to evaluate to 1 in here, and that gives me a contribution of the number of harmonics times the L2 norm of my coefficients. Okay? So certainly I can't expect this bound to be any smaller than f. Okay? Well, for linear operators, I have this great thing called the duality principle, which says that the operator norm of the dual linear operator is the same as the linear operator. And so basically what that means is that if I can switch the order of summation now in a fancier way, then I can get this previous inequality is true if and only if this is true for arbitrary coefficients beta. Okay, now I play the same game. Let's expand the square and look at the diagonal contribution now from when the characters or the harmonics in my family are the same, and I'm going to get a contribution of n. Okay, so by duality, I certainly shouldn't expect this factor to be any smaller than n. So in what this tells you is that the best you can ever hope for is this operator norm should be at most, or the best you can hope for is that it's bounded by the size of your family times the length of your sum. Okay, and that's where this bound is coming from. When this holds, when you have an upper bound like this, I'm going to call my large sieve orthogonal. Okay, and really it's kind of capturing this quasi-orthogonality of your harmonics. To kind of put that into maybe a little bit more geometric language, something from like linear algebra, let's pick out these vectors where I just enumerate, I evaluate the harmonics at these successive integers. Okay, and I form the vectors for each of the harmonics out of these. Okay, if I fix one of the harmonics in my family and I look at the correlation of the vector for that harmonic and the vector for just all of the harmonics, and I look at the inner product, i.e. the thing that measures correlation, and let's say I normalize by just how big the L2 norm is for my harmonic. I'm not going to make any assumption about its size for the moment. We'll do that later. So this thing will expand out the square. It's precisely the thing you get in the large sieve. And maybe for the moment, let's assume that my sum is not too long. Let's say it's less than the number of harmonics. Then what are we really saying here? We're really saying that these normalized correlations, these are bounded on average. Okay? And bounded on average basically means you're always not really, but yeah, it's saying that these things do not correlate with one another very often. Okay? Or at least maybe they do occasionally correlate, but there's very few of them that correlate. Something like this. Sort of, let's say it conversely, just to really drive the point home. By the way, there's a slight typo. This alpha star should be right here, and right here. Apologies. In any case, if many of these vectors, let's say f sub one of them, point in the direction of some distinguished vector, let's say alpha star, and it points in that direction in the sense that the inner product is with a lot of these vectors v of chi, is larger than some constant times the normalized, times the L2 norm of the coefficients, if a lot of them are correlated in this way, or several of them are correlated very strongly, you can violate orthogonality, i.e. the product of these two things is large. So if I have this lower bound by positivity, drop all the terms that you don't care about, and then, you can violate orthogonality. So one of the main ways that orthogonality fails to be violated, or rather kind of the main way, is that your harmonics are somehow biased in some particular direction or set of directions. Okay, that's kind of the idea. So some classical examples of orthogonal large sieves, hopefully well known to many of us in the audience. So you have the classical additive large sieve for Fourier fractions. These are not the absolute best inequalities. You can put a -1 right here, but whatever. Same thing for primitive Dirichlet characters. Here, this is a restriction to coprime residue classes modulo Q. This is primitive characters modulo Q. And I can also make hybrid versions of these. These are what's called translation invariant. It doesn't matter where I situate my interval of length n to get my upper bound. I get the, it doesn't matter where I situate that at. Here it actually does. Here we have to actually situate it down at 1. These fail to be, translation invariant. Okay, but in any case, these are fairly classical. All of this is like the beginning of chapter, I think, 7 of Ivanitz and Kowalski. So you can go read more about this by people who are much more eloquent than I am. Okay.
I have a question. So, as you introduce more averaging, is it considered that it's getting harder or easier?
Yes and no. You introduce, in theory, you're introducing more orthogonality relations, and so you expect to be able to take advantage of that additional structure. But sometimes those orthogonality relations, think about something like Peterson's formula, it's going to kick you out additional harmonics that you then have to deal with, and so you can complicate your life in other ways like that. So it's a trade-off depending on how much you're enlarging your family of harmonics. And please feel free to stop me at any time. Be rude, that's what I would prefer. Just start talking. That's why I tell my students, just be rude boldly. That makes my job more interesting. Okay. Just to give you an idea of how you might prove one of these things, I wanted to do a quick sketch of just the additive large sieve inequality. So just a real quick proof of this. So by duality, it suffices to consider for coefficients that are defined over these Fourier fractions, I just need to obtain this upper bound. Okay, and I'll do a trick that is it's become one of my favorites. Pick out the Fourier kernel. Okay. I guess technically there should be like a 2 right here, but I'm going to just upper bound this by inflating the sum via positivity to just all integers weighted now by the Fourier kernel, and maybe with an implied constant that's changed slightly. I'm not going to care about implied constants in this talk. That's a little bit too much for the context of what I'm talking about, but in any case, we'll ignore implied constants. Okay, expand the square and execute Poisson summation. So if we do that, we get the Fourier transform, and the real great thing about the Fourier kernel is that its Fourier transform is compactly supported, and in particular it's supported on -1 to 1. Okay, so I'll slap absolute values around my coefficients here, and what's great is that because this thing is compactly supported on -1 to 1, if I assume that n is maybe bigger than my family of harmonics, if it's not, you can kind of just prove things directly, inflate the sum to all A mod Q and apply actual character orthogonality. It'll kick you out the right thing. So if n is bigger than Q, then actually the only thing that is you don't even bound it, it's just killed off completely by the Fourier transform. It's everything but the 0 harmonic. Okay, now what is this measuring? Well, this thing is supported on -1 to 1, and so let's Cauchy again. You technically lose something, but in this case it's fine. Cauchy again, and now what are you left with? Well, you have basically everything you want. You have the L2 norm of your coefficients times this function d, defined for the particular fraction a of q, a over q, and it's counting the number of the Fourier fractions that are close to it, i.e. a 1 over n. Okay, and so I've labeled it d because these functions will come up throughout the talk, and damn, do they make my life hard sometimes. So we'll see them more. Okay, so now the only thing you need to do is give an upper bound for this arithmetic coefficient d. Okay, well, you do a simple spacing argument. Fourier fractions are very well understood. Fourier fractions of order q are spaced by 1 over q squared. And so, well, certainly there's one guy in here. It's just the guy that's like the diagonal contribution. It's the same as the A over Q right here. I get that guy, and then I get the total length of my interval I'm considering divided by the spacing. Okay? And then multiply that through by n. There you go. That's your upper bound that you were looking for. Up to the implied constant. You can do better. I'm not going to. Okay. So, observation is that you can sometimes capture the sort of underlying arithmetic of your family of harmonics by doing an argument like this. So you can introduce this coefficient d that will kind of capture the arithmetic of your problem. Okay, and this will come up a little bit later on in the talk. Okay, so for the rest of the talk, I want to consider various large sieve inequalities that are not orthogonal. So when can you not prove that the upper bound that you think should be true is actually true? I want to discuss when that orthogonality fails, why it fails. Is it conjecturally orthogonal, or is it provably not orthogonal? Alex, in his talk, mentioned the cubic large sieve. That'll make an appearance here. I'll maybe keep my comments limited about it since he already spoke on it. And then in addition to kind of talking about the large sieve estimates, I want to show you an application or some semblance of an application where you would go to apply these large sieve inequalities, and you need to wrestle with the fact that you don't have an orthogonal large sieve. So what do you do to overcome this fact? Okay, just like any hardship in life, how do you persevere through it and make progress? Or sometimes you just cry. But either way, I'll show you cases where both are true. Okay, so the first thing that I'll talk about is Heath Brown's large sieve for quadratic characters. Jesse talked about this in his talk, where he kind of just swept this m into the epsilon under the rug. I care about it. I care about the m into the epsilon. So in this case, the large sieve, this is the Kronecker symbol, Legendre symbol, whatever one you want to pick. And maybe this is a sum over fundamental discriminants. Okay? So we get what you would conjecture to be the optimal large sieve up to the m into the epsilon term. Okay? As an application to moments, I said moments of L functions. I've fulfilled my duty now for this conference. So as an application to a couple of moments, let's maybe pick out your favorite modular form of weight k, level, whatever, I don't care. Pick out your favorite holomorphic modular form, twist it by, let's say, a quadratic character with a specific form, just to make my life easy. I can get an upper bound of the correct order of magnitude up to the epsilon term using something like this. And then I can also do the same thing, but for the fourth moment of, let's say, quadratic Dirichlet-L functions. Okay, I can get an upper bound of the correct order of magnitude up to this epsilon term. And I don't like the epsilon term, so we're going to work to do better. Okay? I should remark, by the way, that I don't know if this is conjecturally optimal or not. Maybe someone in the audience knows this, but I don't know if you should conjecturally be able to remove this. Is there some sort of very clever coefficient sequence you can cook up where you would genuinely have this here as like a lower bound? I don't know. It's not known to me. If someone wants to ask during the questions, there is another large sieve estimate where a factor like this shows up, and it is optimal. It is genuinely there, at least for truly arbitrary sequences. And someone can ask about that in the questions if you'd like to see it. Okay, so the point with the large sieve for quadratic characters is we can improve this for specific choices of our coefficients. And this is going to be a theme throughout this talk. So Shan and Lee, back in 2024, he was able to do this for the Fourier coefficients of modular forms. So if I take these to be my special coefficients, I can remove the epsilon term. And I can get an optimal large sieve estimate where the L2 norm here is just of size 1. Okay? Later on, myself and Chanli Shen, we used those ideas, albeit in a slightly more complicated way, because this thing oscillates, this does not, so there are extra complications. But in any case, we're able to also show that we get an optimal large sieve estimate when you are dealing with very specific coefficients.
That log factor is optimal?
Yes. In this, well, if I look back to here, so calculate when this is like tau of n1, tau of n2 over square root of n1 and 2. Yeah, that's what you get. Okay. So both of these previous examples, so how do you actually do this? How do you overcome this non-orthogonality, albeit very minor non-orthogonality? How do you overcome this for specific coefficients? In our case, this relies fundamentally on the fact that you can do harmonic analysis on both variables, i.e. these things both come from L functions. Okay? So I'll give you a brief sort of indicator of this. You might have seen this if you've seen other talks that I've given. You've seen a more elaborate discussion of this. But there's two kind of key ideas for how you can improve the estimate. One is you take your family of harmonics and you embed them into a larger family. What I've written up on here is a complete lie, but it's morally true, so you can kind of accept this. So you slightly enlarge your family. In practice, this is a constant. But in any case, the outer sum is now longer than the inner sum. And so you play this game of leveraging harmonic analysis in both variables. So I expand my square, I apply Poisson summation. It's going to take me to a sum where, let's see, the conductor should be m squared and the length is ml. So the new sum should have length m over l. I Poisson, and then now the inner sum, now the outer sum is shorter. And so now I leverage harmonic analysis in the inner sum via the functional equation. Because these things come from an L function, I can leverage the additional structure there. And then, I'm now smaller again, and you keep playing the game back and forth. And this is ultimately how these estimates are proved. But it relies fundamentally on the fact that you have the additional structure afforded you by, essentially because you have GL2 coefficients, and you can work with those things. Okay? So the point is that when you have a non-orthogonal sieve, you can overcome this sometimes by just working with specific coefficients and exploiting the additional structure that you have there. Okay. One additional observation that I'd like to make is that you can do it even a little bit better. So one, if I know that the divisor function is like log n on average over n, okay? Whereas if I sum up all the integers of size like square root n and then square that thing, it's of size n. Both of these are a sum over integers of size n of some arithmetic function, except that this one is only considering pairs of balanced divisors. And it turns out that this log n really comes from the fact that you have a few exceptional integers which have a lot of unbalanced divisors, and that's what's giving you the log n factor. So you can leverage this additional convolution structure where instead of considering a large sieve estimate, I don't know what you would call this. It's not a large sieve anymore. It's just a fourth power bound. But anyways, you do a similar kind of thing, and if you work with this object instead, you can leverage the additional sort of convolution structure to drop your power of logarithm by a little bit. Okay? And in our actual paper where we use this, this allows you to get, let's say, more main terms in an asymptotic expansion for a moment of functions. Okay? So, this is an additional sort of trick that you can maybe sometimes take advantage of if you have additional sort of convolution structure here. Okay. I'll briefly talk about cubic characters. So Alex did a great job of introducing these things. I won't dwell on the cubic residue symbol here. There's the definition. And the Keith-Brown's large shift for cubic characters gives you the optimal thing. I'm not going to, I also don't know if this term is conjecturally optimal here. I have even less intuition about that. But you have this additional factor that you think shouldn't be there. And in fact, Keith-Brown, it's already been quoted, but he makes this quote that it seems possible you could remove this with more effort. This turns out to be very false. You cannot remove it with more effort. So Alex and Max, back in 2021, they, assuming GRH for Hecke L functions, showed that you can make some choice of coefficients, maybe where m is a little bit bigger than n, and you can get a lower bound of where it shows this term is necessary. It has to be there. Okay? And Alex, is this still conditional on GRH, or is this like forthcoming work? I don't know.
He knows the right questions to ask. Yeah, so if you're willing to wait a few weeks, I have a joint paper with Alex Lefebvre and Jeff Hofstein that should make this unconditional and also say some more about high-dimensional, high-order systems.
Yeah.
So,
very exciting. Sorry to put you on the spot.
yeah. That wasn't planned, by the way.
I also didn't indicate which Alex I was talking to. So, either way. Okay, anyways, how do you actually sort of concoct these coefficients? Well, they're really built out of cubic Gauss sums, or rather conjugates of normalized cubic Gauss sums, whatever. And so what this is telling you is that the cubic residue symbol in this kind of odd way is biased towards cubic Gauss sums, or correlated against, or however you want to kind of say it. Or rather, maybe there's a bias in cubic Gauss sums themselves, and that's kind of what the title of the paper is that they put on. Okay, so in any case, yeah, you have this non-orthogonal large sieve. It fails to be orthogonal not for some sort of silly reason, but for actually a fairly deep reason, that you have this bias in cubic characters. Okay, just to kind of show you how this kind of plays out. Again, Alex already talked about this in his talk. We were able to prove an asymptotic formula for the second moment. I guess there should be a smoothing function here. Ignore that. We're able to get an optimal error term, and really the cubic large sieve, here it's not really something we overcome, it's just something that imposes a fundamental limitation. So you cry for a second when you realize this, and then you work around it, you work to overcome this. So it's kind of for the reason that the cubic large sieve is non-optimal, is the same reason on some level that this error term is optimal. And in fact, we conjecture that there should be a second lower order term of x to the 5/6 times some linear polynomial in log x, and then something that's little o of that error. Okay, so yeah, here the large sieve, the non-orthogonality, it's not something that we sort of overcome or work around, you have to work with it, and it's really telling you something deep about your problem. Okay. So as another example of a case when we have a non-orthogonal large sieve and the coefficients are going to kind of point in funny directions, or the harmonics are going to point in funny directions, I'll consider holomorphic modular forms of weight k with respect to gamma 1 q, which decomposes in this way. We've had enough discussion about this already. I won't belabor the definition of holomorphic modular forms. I'll normalize them so that their first Fourier coefficient is 1. And here's the Fourier expansion for it. I'll build my L functions out of these if I need to. And I'll make the following observation, that if I look at the whole sort of basis of these guys over all of the characters, there's about q squared forms. Okay? I'm going to normalize my sum in two ways. I'm going to normalize by the number of characters that I'm considering here, and I'm also going to do a harmonic average. This is like dividing by this squared L2, the squared Peterson inner product norm of the modular form, which is like generally at size q. So generally, you would expect that something like this, if these are sort of genuine harmonics that would obey a large sieve inequality, you would have an upper bound like this. I have a 1 over q squared coming from the two normalizations, the number of forms in my family, and the length of my sum. Okay? This is what you would naively expect to be true, and you naively expect it because it is very wrong. This is, it fails to be true for quite dramatically, actually. Also, I'm just going to call this thing B so I can reference it on the next slide, so this thing. So yeah, this is very false if you are considering truly arbitrary choices of your coefficients. So Evanietz and Lee in 2007, some pretty classical work now. You don't need to parse all of this. I'll simply say that B is translated into a sum over something where you have a new family of harmonics, and those harmonics are products of Kloosterman sums and Bessel functions. Okay? So again, don't need to parse all of this, but this is equality. This is not an upper bound. Okay? So you can make this large by selecting a certain T and H, and if you'd like to see how exactly this is done, go read Evanietz and Lee's paper. But let's say for n a little bit bigger than q, let's say h is like a small power of q, I can pick a particular sort of product of Bessel functions and Kloosterman sums, and I can get that this thing is bounded by like a power of q. Okay, well if n was like less than q squared, which I just said it was, this thing should be like bounded on average. So what we're saying here is this thing is absolutely massive compared to what you would expect, especially since q is tending to infinity. So in a very sort of odd and counterintuitive way, perhaps, a very surprising, well, perhaps beautiful way, Fourier coefficients of cusp forms, they tend to point or are correlated with products of Kloosterman sums and Bessel functions. It is a highly non-obvious but amazing fact. And to a pretty large extent, you can make the correlation rather large. So, you can have these Kloosterman sums and Bessel functions sort of, or rather the Fourier coefficients pointing in these directions. So it's a rather, surprising phenomenon. Okay, as an application to L functions, it's some, yeah, absolutely.
Is there something that mentioned in Evanietz, Liu, and Sarnak, where they look at kind of bias with E of root n?
That's on the primes.
That's not a price.
That's on the primes.
Is that
It's on integers too.
It is?
Yeah.
I'm not familiar enough with that paper to comment intelligently on it, so I'm going to not answer that question.
So you're not going to comment unintelligently?
No, I'm not going to do that either. Better to what is it? Keep quiet, or rather than speak and remove all doubt of being a fool, or something like this. Anyway.
It's like Matt wants to say something.
It's the same. I think it's the same. Like take t0 equals 1, and then the Klosterman sum is 1, and then you just have the special function, which is like e of 2 root n, or take h0 equals 1 or something. I don't know. I think it's the same fundamental thing, that it's they correlate with e of root n times stuff.
I'm gonna let y'all talk about this after my talk. Okay?
Related to your talk.
Yeah.
If you see this bias in this GL2 family, then how come you can't cook up a bias in, like regular GL2 spectrally complete family?
I'm not sure I understand your question.
Like if you just take family of holomorphic forms of weight k,
Yeah.
you have an optimal large state.
Right. I'm not sure. I don't have a good answer to that at the moment. We can talk more about it after the talk. Yeah. Okay. Yeah, we'll get around to that maybe later. Well, let me talk about how you can kind of apply this, how it kind of manifests itself in application to some moments of L functions. So let's pick out k greater than or equal to 3i. Let's send q to infinity. Let's just let it be a prime, by the way, to make our lives easy. Everything's a new form, and such, blah, blah, blah. Jankovic back in 2011 was able to show that the sixth moment of the L functions attached to these guys obeys the conjectured upper bound up to q to the epsilon term. And likewise, Phi Shandy and Sean Lee in 2020 were able to do the same thing for the eighth moment, albeit it's much harder in that case. And we would prefer asymptotic formulas, though. Come on, that's what we would kind of prefer. So if you include an additional average over the critical line, you can get an asymptotic formula for the sixth moment. Now you have the right asymptotic. You have a log q to the 9 times some constant c. And in ongoing work with myself and Alex Dunn, we're working on the eighth moment, and hopefully soon, 1 log q away, we'll have an asymptotic formula for the eighth moment as well. So in all of these, I want to talk about just kind of what goes into proving something like this. So if you reduce via the approximate functional equation, morally you need to understand a sum that looks like this, where your n's are maybe of size q to the j over 2, j being 3 or 4, depending on which moment you're looking at, of the divisor function times the Fourier coefficient of your modulus form. So to succeed, you kind of need to say that your divisor function doesn't look like a product of Bessel functions and Kloosterman sum, right? You need to say that it doesn't correlate with the Fourier coefficients of Gus forms. Okay, well it shouldn't, but like, how do you actually say that? How do you actually prove this? And the key tool is you just use a trace formula, i.e. you Voronoi on tau 3 or tau 4. Okay? And some these kinds of a trace formula, these will often introduce some different family of harmonics that you have to square with. So in our case, I'll just look at the case of GL4. The application of Voronoi to, let's say, the divisor function times an additive character, which is what's going to happen when you apply Peterson and he kicks out Kloosterman sums and you do some manipulations. You have to apply Voronoi to this. You're going to get these sort of hyper-Kloosterman sums indexed over the divisors of your function, over a fourfold divisor sum here. Here I'm normalizing. This isn't actually what we have in our paper, but for simplicity, I'll just normalize here. This is what the Bay bound would kick out for you. At least that's what you would think is the optimal thing, so that's the appropriate thing to normalize by. So we are able to prove a large sieve for these harmonics. We're able to prove that if you sum up, just in the exact way that we did before with the additive large sieve, we're able to get, well, the number of guys we have times the length of our sum. Damn. We get another guy. This is he's a very peculiar specimen in that so we get a tau 4 squared, and that's not surprising. Here's tau 4 sitting right here, and it's being squared. Okay? So that's not surprising that we get that factor. What's maybe a little bit more surprising is that you get a sum, ignore the little b squared right here, that's not super important, but you get a sum over cube divisors of n, and you get a factor of c, the cube root of whatever that divisor is. And so if you're working, say, on a small enough interval, this thing can fail to be orthogonal because this function can spike at an integer that happens to be divisible by a large cube. Okay, that shouldn't happen often, but you kind of have to reconcile with this fact. So I think maybe I'll skip this slide. If someone wants to see where that factor comes from, I can do this calculation for you later. It's not super long, but if anyone wants to see it, you can ask me during questions. Okay? I just want to make sure I cover everything that I want to talk about. So yeah, I'll note that this function is bounded on average. If you actually just look at like trying to calculate the average value of this thing, okay, it shouldn't actually pose a problem. But sometimes you still want to split into short intervals. You want to apply this large sieve inequality in a setting where you've had to split your intervals into somewhat short intervals. And an example in the eighth moment is where we need to control the oscillations in a particular integral transform. And maybe I have something where here's the sum over my harmonics. I actually have two sums where I'm going to eventually Cauchy and split it into something where I can apply the large sieve. Here are my Kuiper-Kloosterman sums, and I have an integral transform where in order to try and control the oscillations of this guy, I may split M1 and M2 into short intervals to maybe control the remainder term in a Taylor series expansion, something like this. Okay, hopefully it's kind of believable that splitting into short intervals would be a way that you could possibly control something like this. Okay, well, I don't want to split into short intervals, so I'll cheat and I'll prove, maybe steal, from our good friend Matt here. If you use, so he has a lemma where you can prove kind of a hybrid version of this where you include an additional sort of oscillatory factor in n that's like exponential like this. And yeah, thankfully his machinery goes through almost unchanged, so we're able to freely pirate from our friends and make progress on a problem. And now notice here I haven't had to split into short intervals. I have the full interval, and I can take advantage of the average value of this thing, and that kind of overcomes the non-orthogonality. Okay. One maybe final example, and I should have time to go back and maybe show a couple of things, but I want to show you a very curious example where I would conjecture that the large sieve is optimal, but I don't know how to prove it. So this kind of goes all the way back to my PhD dissertation, but let's just think about the Gaussian integers. I'll pick out one of these sort of angular Hecke characters. This, you can define it on, since it's a principal ideal domain, pick out any of the generators. The 4 here makes it independent of the generator you choose for your principal ideal. So this is genuinely a character on ideals only. And you can ask about large sieve inequalities over the Gaussian integers for, expressions that depend on these characters. Okay, well, it's not too hard to show that you have an optimal large sieve when you're just considering those guys. That's not too hard of an argument. And you also have something where, if you want to do it against an Archimedean character with just like a Dirichlet polynomial, this is pretty classical. This is just the same method that you would use in the integer case. So we have optimal large sieves here. But it turns out when you want to do something like calculating you're trying to show that prime ideals equidistribute in sectors, you need to consider both of these kind of parameters simultaneously because they can be used to define a sector in the complex plane. By which I mean like 2 radii cut by 2 anguli. Okay. So maybe I want some sort of hybrid large sieve estimate like this, and hopefully it's clear that this is the thing I would expect on the right side. I have the number of harmonics here. Maybe I can turn this into a discrete sum at some small cost, whatever. In any case, I have about MT harmonics. Okay. Well, the trivial upper bound, if I just apply like one of the large sieves from the previous page and then estimate the other sum trivially, then this is the bound I get. The MT factor is correct, but I have this minimum of M and T here, which is not quite what you want. So there's another way that you can do this, and this is due to Coleman back in '89. He is able to get the MT plus N term, but you can tell by the incomplete parentheses, I'm hiding something from you. So you get this extra factor of n to the 1/2 times n plus t. Kind of odd. Okay, let me show you exactly sort of where that comes from. Why does that come up? Before I do that, I guess I do want to make one sort of observation that I still don't know quite what to do with. I don't know if it's substantive or not. So I can Cauchy this thing, and it's bounded by m squared plus t squared plus n. And an observation is that I have about MT harmonics, but if I look at the L function associated to this harmonic, and maybe the square because I'm squaring things here, the conductor of that is m squared plus t squared. And so there's this mismatch between the number of harmonics I have and the conductor of the relevant L functions. And so I don't know of very many places where something like this happens. I think Anurag Sai was telling me about one example. It slipped my mind now, but I know there's maybe some other slight example where this happens. But this sort of mismatch doesn't happen often. So maybe in some sense, maybe your large sieve factor, when your coefficients come from an L function, maybe it should be replaced by the conductor instead of the size of the family. I don't know if that's true.
What happens with the family of elliptic curves, right? We expect they're like Q to the 5/6 elliptic curves with conductor to Q. So there's a little bit of mismatch.
Okay, interesting. We should talk more about that later. Anyways, yeah. So dang, got him again. Okay. Anyway, so the reason that non-orthogonality comes up, if you sort of sort of apply the quasi-orthogonality relations that these impose, you're able to get something where you kind of expect this to be the right thing, except that you have this additional arithmetic coefficient where what it's really doing is counting lattice points inside of the sector. Okay? And D of A is counting the lattice points where your outer and inner radius are like this norm of your fractor A. The total radius is like norm of that over T, and then your angular sort of constraint is about size 1 over n. So the area of this thing, well, you can always kind of get one or maybe a bounded number of guys that you have to account for. And then you just multiply sort of everything around, and this is the area. And if I multiply this by MT, that's the right thing. That's what I would expect. What causes you issues is the perimeter. Sometimes, if you're sort of pick your ideal A to be, I don't know, somewhat degenerate, you can dominate the count of the number of lattice points in this sector by the perimeter instead of the area. And so you have to account for this term. So that's really where this non-orthogonal term is coming from. And the thing is you don't expect this to happen often. And so somehow, if you wanted to prove an orthogonal large sieve, you would need to obtain like a pointwise bound that really reflects like the average of this thing over all ideals. And I don't know how to do that. And maybe it's truly not orthogonal because this thing can genuinely spike. It's not clear to me exactly if that's true or not. But in any case, this is an example where orthogonality currently, at least how we know how to prove the large sieve estimate, orthogonality fails, but it seems conjecturally that it should. Anyways, how do you actually account for this in an application? Let's maybe say if you're doing something like large values of Dirichlet polynomials, you might want to estimate something. You might want to use an estimate like this. And the idea is that you just use your two bounds that you have. You have this trivial bound coming from the two actually orthogonal large sieves, and then you have this hybrid estimate that has its own kind of failures. And the idea is you just interpolate between them. And so let's cook up this parameter here. This is going to measure sort of how far apart m and t are from one another. So if m and t are the same, this is 0, and m and t are at most, this parameter is at most 1. So this is some real number between 0 and 1 that's measuring the spread of m and t. Just to be clear, you can relate the minimum and maximum of m squared and t squared to this parameter in this way. Okay? And the idea of how you might actually make this work is you split it into cases. If L is small, then this thing is close to being optimal. Okay? So if m and t are close together, then this thing is close to being optimal. But if m and t are far apart, that forces one of m or t to be small. And so then this estimate is the one you would want to use. I guess when you're working with maybe estimating large values of Dirichlet polynomials, you can regulate with taking a power of your zero detecting polynomial. And this extra flexibility, along with interpolating between these two bounds, actually allows you to recover a result that would give you what would be as strong as if you had an optimal large sieve. So you can actually overcome non-orthogonality and get something that's just as strong by leveraging an additional sort of pair of large sieves. Okay. Yeah, the point is that we can sometimes overcome this by sort of interpolating or combining large sieves. Okay. So just main takeaways from this talk. Like children, every large sieve is unique and requires special love and attention. Okay, so you really have to give your love and care to each of them. Also, like children, large sieves can be counterintuitive and surprising and frustrating, but in doing so, they teach us something about themselves and about us. Okay? Unlike children, you can ignore them if you want to discover something else. I would not advise this with actual children. Okay? I've got a little bit of time left, so maybe let me go briefly talk about where this sort of factor, this arithmetic factor, comes from. How does this sort of c cubed pop up here? So here's my hyperklusterman sum. And here I'm just going to fix some factorization of n into 4 pieces. I'll also fix, let's just consider the case L equals 1 to simplify the notation a little bit. So let's apply character orthogonality in X4, and then it'll kick out this congruence condition. And I would like to reduce this to coprime residues in an attempt to eventually apply the additive large sieve. So if I do that, I'll kick out D dividing Q and just making this a sum over coprime residue classes. This forces a divisibility condition on one of the factors of n. And then the idea is that, well, now my congruence condition is mod Q over D, and so I need to reduce the other 2 factors mod Q over D. So if you do this in the sort of appropriate way, you'll get sort of D copies of some of these orthogonal sums, and you can apply a character orthogonality in those cases, and you'll get this Q squared over D, this D squared factor popping out. And you can kind of imagine that somewhere along the way we can apply orthogonality one more time and kick out a factor of Q over D. That'll give me a Q squared and then the 1D here. And I've forced out 2 more divisibility conditions on N1 and N2. Okay, and so that's where the D cubed, D has to divide all 3 of these factors, so D cubed divides it. So that's kind of where it comes from. So when you start working out exactly how these coefficients work, it's not super surprising that you get an arithmetic factor like this. Okay. I think in the interest of time, I'll go ahead and just stop.
Are there any questions for Joshua?
Okay, I have a comment since you raised the question about the constant and Heath-Brown's quadratic large sieve, or
The epsilon term?
Yeah, so there's some numerics. So I had a student do some numerics, and as far as the numerics were concerned, as far as he could compute, it looks like it could just be like the constant 2 epsilon or something.
Oh, okay. So it seems like it shouldn't be there. Huh.
Maybe.
And I know there's some more work where someone gets an explicit version of this. I know. Yeah, there's a paper. I forget who's it.
I think it's a Jihad Liu. He was was an undergrad of Ian Petra.
Yeah.
Who's now at Stanford, maybe, I think.
Okay.
Yeah, you can replace it. You can replace it with like a appropriate something like log Q over log Q or something like this. Like
I
e
think
to
it's
the
worse.
exponential.
I think it's
yes,
worse.
E of all of that. Yes.
Yeah. So that's what you can prove, but just like what might be the truth, I mean that
Yeah.
the numerics.
There's a recursive divisor process that's happening, so this is the
Yeah.
divisor count, basically.
Yeah.
Are there any other? Oh, yeah.
I want to know what's in slide 33.
Oh, slide 33, sure. It was the case where this Q to the epsilon term is optimal. So if you look at the additive large sieve, but with a square moduli, you can actually show that these, that you do have a genuine Q to the epsilon factor that shows up, and it's really because you can concoct these Q, where you can play this game with the Chinese remainder theorem and make these fractions sort of cluster around 1 over Q, when it's a product of primes.
Page 13.
All right, we're going to go back real quick. Page 13.
Sorry.
I'm a gamer. I can do this.
Yeah, curious that is considering higher power. So if the inner power has the power 6, then
Yeah, this is like a 6, and this is like a tau 3 or something, or
then
like what's this?
Yeah.
Didn't you ask me about this a week ago?
Yeah.
Yeah. I thought I answered it a week ago. It's I think the sort of difference you get here grows, but you can't sort of apply it for larger values of n to the actual moment problem, because the range of n where you would need to apply it starts exceeding where it's actually useful. We can sit down and do a calculation after. But yeah, I think the fact that this is 8 and this is 6, I think this grows to like 15 and 13, something like, I forget. I think the difference grows. Yeah, I know this is an 8 because it's 10 minus 2. And 10 is like 2 times 2 plus 2 times 2 plus 1 divided by 2. Yes, okay, yeah. We can do the numerology later.
Okay, so let's thank the speaker again.